So good evening, gentlemen. We return to Dijkstra's Notes on Structured Programming. This new chapter is called On Our Mental Aids, and here Dijkstra's interest is in studying what does it take to structure a program so that it's easy to reason about it, and in particular so that you can convince yourself of its correctness and convince others of its correctness. You will recall that in the last chapter we were talking about the limitations of our reasoning, limitations of our minds. And the job of a programmer is not merely to produce code. This is very important to understand if you're a programmer or if you're interested in getting into this career and you're looking at the increasingly powerful large language models that are out there. And you ask yourself the question, well, why would I be a programmer? Or what's my value as a programmer? And Dijkstra's contention is the value of a programmer is in his ability not merely to produce code, but to produce code that we know is correct. So it's produce a program together with an argument that the program is correct. And remember that we looked at the question of tests. Many people will say that if you want to know that an LLM is generating correct output, for example, if you ask an LLM to generate for you, this is a stupid example, of course, but it's just meant to drive a point home. So you ask it to generate for you a function or a program that adds two integers. And then you ask it to generate a bunch of tests. So you say you add 10 to 10 and you check that that's equal to 20. And you add 5 to 125 and you check that that's equal to 130 and so on, right? And Dijkstra's whole point is that if you just take the function that you're thinking about or the program that you're thinking about as a black box, and this is what people are really asking us to do when they say, you don't have to read the code, you can trust the LLM. Well, how do you know that if you were to look at the implementation of the function, that you wouldn't find something like a special case analysis? So let's say if x is equal to 10 and y is equal to 10, then return 20. And if x is equal to 5 and y is equal to 125, return 130. Otherwise, return x. Now just note that there's nothing in these tests which would demonstrate that this program is incorrect. And you may say, well, there's not enough tests here. But you can see that even if you had 1,000 tests over here or 1,000,000 tests over here, because this function operates on two integers, which could be 64-bit or 32-bit integers, let's say they're 32-bit integers, then you would have 4 billion possibilities for x and 4 billion possibilities for y. And so you'd have 4 billion times 4 billion, which is a very large number, possibilities of tests that you'd have to write to demonstrate that this program is correct. When we all know that if you just write the code like this, you can immediately see from this code right here that the program is correct for all intents and purposes. And so Dijkstra is asking the question, how do we generalize on this? How do we make it such that even as we write larger and larger programs, we maintain this property that we're able to look at the code structurally, look at the source code, and get the same level of conviction about their correctness as that we have in this program over here, that this add function is correct. So that's what we're looking at in this next chapter on our mental aids. So I'm going to break this down into 3 videos, I believe, because he also breaks it down. The longest one is on mathematical induction, but in this video we're going to get into enumeration. So why should you follow this video? It's really to set up the second and the third section, which are very important. And so I'd encourage you to watch it through and also to think through what he's saying. And don't just dismiss it because it feels simple, because pretty soon things will get very complicated and you'll need to have understood what we said here. So let's get into it. On our mental aids. In the previous section, we have stated that the programmer's duty is to make his product usefully structured. And we mentioned the program structure in connection with a convincing demonstration of the correctness of the program. But how do we convince, and how do we convince ourselves? What are the typical patterns of thought enabling ourselves to understand? It is to a broad survey of such questions that the current section is devoted. It is written with my sincerest apologies to the professional psychologist because it will be amateurishly superficial. Yet I hope and trust that it will be sufficient to give us a yardstick by which to measure the usefulness of a proposed structuring. So now in talking about a psychologist here, what Dijkstra is saying is that the structure has to be anthropological. You have to write the program for human beings to understand it. And that's a truism in programming, that code is written first and foremost to be understood by a human being, and then secondarily to be executed by a computer, because a computer will, once you have a sufficiently good compiler and environment, will execute anything that's well defined. So the reason we go into so much effort as programmers in the way we structure programs is for our own understanding. Among the 3 mental aids available to understand a program or a proof of its correctness, there are 3 that I should like to mention explicitly: enumeration, mathematical induction, and abstraction.